Good afternoon, everyone. Dr. Bennett here. So today we are going to be deriving and analysing the Breguet endurance equation specifically for a piston propeller driven airplane. So just a quick note as to why we have to do this type of analysis separately for different types of propulsion system is that endurance and range depend upon how the propulsion system of the airplane produces thrust, and so the governing equation for range and endurance for a piston propeller driven airplane will be different to that of a jet powered airplane. So to start this derivation, we actually need to go back to the so-called average value method for endurance. So the average value method states that, if I can get the camera to focus, right? The average value method states that endurance is simply equal to the amount of fuel that we have to burn, WF, so delta WF is our fuel load, divided by the rate at which we're burning it. So WF dot is the rate of fuel burn. So if, for example, our fuel load is in kilograms and the rate at which we're burning fuel is in kilograms per hour, for example, then the units of this equation will be kilograms over kilograms per hour, which will give us an endurance in hours. So this dot notation here is just shorthand for a derivative with respect to t in the usual way, right? So this is just dWF by dt. And so depending on the propulsion type of the airplane, in this case piston propeller driven airplane, that will depend on how quickly we burn fuel, right, as a function of some properties of the engine and in this case the propeller efficiency factor. So for this case, this WF dot term will be equal to our brake specific fuel consumption, C for short, over our propeller efficiency factor, E to prop, multiplied by the average power provided by the engine. So this power term here, this is the power required to overcome drag. So if power if power is just force times velocity, then this is just equal to the average drag that the airplane experiences multiplied by our true airspeed. Power is force times velocity. So that all of that means that we can write our endurance equation for the average value method as delta WF over C over E to prop d average true airspeed. So that is the so-called average value method for endurance. Now, the main problem with this, and the reason why we're going to extrapolate this into the Breguet method, is that this equation does not take into account a change in velocity due to a change in aircraft weight. So we know, so let's go back and see what I mean by that. If we go back and look at our lift equation, lift is CLQS, where Q is our dynamic pressure, 1/2 rho V squared. For a cruise problem, and by cruise I mean flying at constant altitude and constant speed, so if we're flying at constant speed, that means that thrust is equal to drag, and if we're flying at constant altitude, that means that lift is equal to weight. then this equation can be formulated in terms of W, because as we just said, if we're at constant altitude, lift is equal to weight. So we can rearrange this equation for V as a function of W, and that will highlight the issue associated with the average value method. So rearranging this equation, we will get V is equal to, let's see, 2W over rho SCL, all square rooted, right? Now, this shows us the problem with the average value method. And so in this cruise problem, this endurance flight, we are burning through our fuel load. And so the aircraft is getting lighter. And so if the aircraft is getting lighter, the speed at which we should trim at to achieve best endurance will get slower, right? As W decreases, V should also decrease to compensate. And this equation does not take that into account. And so that's the reason why we're going to extrapolate this formulation into the so-called Breguet method to basically correct for that and make this whole approach a little bit more accurate. So what we're going to do is, for our Breguet endurance equation derivation, we're going to integrate, instead of having this delta WF term in the numerator, we are basically going to integrate this part of the equation, d average V. Instead of having the delta WF term on the top, I'm going to integrate this between two specific weights, W2, W1, with respect to W. So W1 is our starting weight, W2 is our ending weight, and because W2 is always less than W1, we need a negative sign over here. So basically, if we perform this integration now, that should lead us directly to the Breguet endurance equation for a piston propeller driven airplane. To get started though, however, we're going to need one small kind of mathematical trick to get us started, and that is to essentially multiply this equation inside the integral by 1 in disguise. So I'm actually going to multiply this term by L over W, which is 1 in disguise, right, as we showed over here. So if W equals L, then L over W equals 1, right? So that will get us started. Negative W2, W1. Then I'm going to flip this so that it makes a little bit more sense. Then I'm going to group together L over D, so from here this term with this, and then I'm just left with, of course, 1 over V W dW. So from here we can take out all of the terms from the integral which do not depend on W, and that's basically all of this stuff here. So of course the propeller efficiency does not depend on the weight of the airplane, neither does the brake specific fuel consumption, because that's just a feature of the piston engine, and neither does lift, because it should be constant, and so should D. So I'm going to bring all of that stuff outside of the front of the integral. And the other thing I'm going to do to basically make this a little bit more generic is convert the magnitudes of lift and drag into coefficients. So L over D is equal to CL over CD, because the magnitude of L and D are both non-dimensionalized with respect to Q and S, like up here. So the Q and S's will just cancel from that, right? So that leaves us with something that is a little bit more manageable. And again, the reason why I haven't taken out V from here is because, as we showed up here, v is a function of w, so of course we can't bring out the airspeed term from the integral. So we should be in pretty good shape now. We're going to take that equation and we are going to integrate, we're going to integrate this term here, but before I can do that I'm going to have to replace v with this expression here, the one that is a function of w. So that's going to look like CLCD W1 W1 on the bottom, W2 up here. Then I'm going to replace that v term with this expansion, WDW. So I've just replaced this equation for v, which came from the lift equation, into here. Right. Now again, I have a bunch of stuff that I can take outside of the integral because it doesn't depend on w. So let's do that real quick. Negative eta p over c. Then I've got rho s over 2 square rooted, and then I'm going to group this CL with this CL right here. So when I bring this out with the square root, that will give me CL to the 3/2 over CD. And then I have this square root of w multiplied by this w right here, so that will give me 1 over w to the 3/2. And then finally, I think I'm in a position now where I can just go ahead and directly integrate this equation. So let's see what I'm going to get. P of C, rho s over 2 square rooted, CL to 3/2 over CD. So this is essentially 1 over w to the 3/2 is the same as w to the negative 3/2, right? To integrate, add 1 to the power, divide by the new power. So this will give me w to the negative 1/2. So I've added 1 to the power, divide by the new power. So divide by negative 1/2 will give me that, right? Evaluated between w1 and w2. So a couple of things I can do right here just to tidy up. That negative will cancel with that, and I can also bring the 2 out. So let's bring this 2 out and let's push it inside of this square root here. So if I put this 2 inside of the square root, I'll get 4 in the numerator inside divided by 2. So 2 rho s eta prop over c, CL to the 3/2 over CD, and then this final term will just be w2 to the negative 1/2 subtract w1 to the negative 1/2. Or if you prefer, 1 over w2 square rooted subtract 1 over the square root of w1. However you prefer to write that. But this right here is the Breguet endurance equation for a piston-propeller aircraft. So let's just have a quick look at what this actually means in practice and how we can go about maximizing endurance for our airplane. Well, if we are trying to maximize endurance, that means maximize things that are in the numerator or minimize things that are in the denominator. So let's start here. So to maximize endurance, we're maximizing air density. So that tells us that for a piston propeller driven airplane, maximum endurance should be at low altitude because air density is greater at lower altitudes. We also get maximum endurance if we maximize our wing reference area S, obviously maximize our propeller efficiency. So this is always a number between 0 and 1, right? Because it's a propeller efficiency factor. So a good propeller efficiency is probably somewhere between 0.7 and maybe 0.85, something like that. So then moving on to maximize our endurance, we should be minimizing our brake-specific fuel consumption. That seems fairly intuitive, right? We're going to be maximizing this ratio. We'll come back to that in a minute, because this is not just like a direct lift to drag ratio, because we have this CL to the 3/2 in the numerator. So we're going to come back to that and have a look at a bit more detail about that. And then, of course, to maximize this final term is just simply to maximize our fuel load. So if we carry more fuel, we'll get more endurance, obviously. So let's return to have a look at that term specifically. So we're saying that endurance is max when this term is maximized. Now, mathematically speaking, that's equivalent to minimizing its reciprocal, isn't it? So let's say, or when CD over CL to the 3/2 is minimized. Now, why have I done that? Well, I know how to find the minima of a function. I can just differentiate it, set it equal to 0, and then solve it. So let's work on that just for a second, and that's going to lead us to a very interesting result. So let's basically expand out this ratio. So if we've got CD in the numerator, CD is equal to CD0 plus K CL squared. So this is the parasite drag coefficient plus the induced part. So that's basically just an expansion for the total drag coefficient here. And then I've got my CL to the 3/2 in the denominator. So let's break that up so it's a little bit easier to differentiate. So K CL to the 1/2 once it cancels. And like I said, what I'm going to do is minimize this function by differentiating it and setting it equal to 0. So I'm going to differentiate it with respect to CL to 3/2 plus KCL to the 1/2, set it equal to 0, and that will tell me where the minima of the function is. So let's see what we get. Differentiating this term with respect to CL will give me -3/2 CD0. So take 1 from the power, CL to the 5/2. And then this one is easy, right? 1/2 K CL to the -1/2. And we're setting that equal to 0. So solving this, let's see, if we take this term to the right hand side, so I've got basically adding this term to both sides, 3/2 CD0 over CL to the 5/2. Now if I multiply both sides by 2 and also multiply both sides by CL to the 1/2, hang on, let's do this the other way around. Let's multiply everything by 2 and let's multiply everything by CL to the 5/2, and that will give us KCL squared on the left side and 3CD0 on the right side. So this is our parasite drag coefficient, and this is our induced drag part. So basically, to achieve maximum endurance is to attain the condition where the induced drag is 3 times larger than the parasite drag. This is parasite drag, this is induced drag. So to achieve maximum endurance is to attain the condition where induced drag is 3 times larger, because we have this factor of a 3 on the right side. So 3 multiplied by the parasite drag gives us the induced drag, aka the induced drag is 3 times larger than the parasite drag, and that is going to maximize endurance, as we've shown, to maximize that ratio of CL to the 3 halves over CD. Good, so that is the Breguet endurance equation, specifically for a piston propeller driven airplane. In the next video we will have a look at the Breguet range equation for a piston propeller aircraft.